Our next speaker is Chris Manning. Chris is a Thomas M. Siebel professor in machine learning at Stanford University and the director of the Stanford AI Lab. And he has done extensive research across a broad range of topics in NLP, including question answering, machine translation, dependency parsing, and computational linguistics. And he was the past president of the ACL, and I'm also very fortunate to have him as my advisor. So without further ado, let's welcome Chris.
Thank you very much. Okay, so for today's talk, what I wanted to do is talk about making the L in VQA matter. Now, of course, there's an immediate objection to this being the title of the talk, which is there is no L in VQA. That's an unfortunate fact, but if you look at it a little bit more, well, really, the Q&A are both language. But I actually want to get a little bit beyond that. And what I want to do in the second part of the talk is motivate the idea that for making further progress in tasks like visual question answering, what we want to be doing is more explicitly building a language of thought, which then covers all of VQ&A. And as a subtext that goes along with this, I think the VQA community has been pretty much dominated by vision people, and I've got nothing against vision people. But, you know, somewhat fortunately, things have gotten a lot easier these days. So, you know, even I can fire up PyTorch and load up a faster RCNN model. So I think there would actually be a lot to gain by getting more involvement from people from language and reasoning communities as well as vision community in looking at some of these problems of image interpretation, because I think there's sort of interesting work to be done there. Okay, so in this talk, I'm going to sort of proceed backwards through the letters A, Q, V. So let's start with the answers. I think most of you know the situation with answers pretty well for the VQA version 2 data set. So about 38% of them are yes, no. Then there are the common numbers. This shows the patterning of our evolved human cognition. The common answers have factors of 4 and 6 in them. 5 and 6 in them once you get past the small numbers for reasons of time and other things, 11%. And then there's sort of answers that are a small set of semantic types, objects, activities, spatial, left, right, animates, locations, materials. Just about everything falls in a few classes. And so basically the answers are nearly all one-word stuff. And so you could react that this is not exactly human language in all its grandeur. There is some other stuff, so you know, there are compound nouns like tennis racket, there are adjective nouns like barbed wire, some color combinations, red and white, activities, playing Wii. I guess it was when the MS Coco data was put together, but there's an amazing amount of Wiis in the MS Coco data set. There are some locatives on plates on sidewalks and some sort of object combinations like fork and knife, ketchup and mustard. But this is still pretty simple language, and a lot of it is kind of calc language, right? So a lot of the things like ketchup and mustard or black and white or barbed wire are really sort of fixed calcs. They're not really compositional language. And so you could then start wondering, is there interesting stuff in the answers? And the answer is sort of barely, right? So there's some located objects, man on right, one on left. There are a few things like purposes, to catch frisbees, to catch a ball. There are some longer phrases that come from the OCR quotative things like what's on signs, but they're not really interesting language in my sense. There are a few cases where there's really interesting language. So there's a question of why are there no utensils, and there are answers like you can eat pizza with your hands, do not need them. But well, the problem is that those are all singleton answers with which each one of the 10 people answered something different, and so effectively these answers don't play any role in the task because most systems use something like the 8 occurrences cutoff, and none of that stuff appears. So this seems a little bit bleak for language. The question is whether there's anything to change. Should we do real natural language generation? Well, of course, one of the tasks is doing real natural language generation, and there's been the Visual Dialog challenge for the last couple of years. But perhaps the problem with that mirrors exactly the same problem with all dialogue work in natural language, is evaluation is really dire. So if I just go to the sort of natural language case, there's this kind of nice results from work by Novikova et al. And so what these are showing is in the top left, it's showing automatic metrics of evaluation and how well they correlate with each other, and they all correlate with each other really well, apart from the 11th one down the bottom, which is just the semantic similarity. And then down in the bottom right, there are 3 measures of human evaluation, and they correlate with each other really well as well, especially the bottom 2, naturalness and overall quality, which are the main ones that are used in practice. But then if you look in the bottom left, and you say, do the automatic and human metrics correlate? Really not very much at all. And so effectively, sort of, you can't do anything very meaningful with natural language generation using automatic metrics. And in the Visual Dialog challenge, that's sort of partially dealt with by asking for a ranking of 100 candidates. But, you know, I'm going to just go for the let's avoid it answer and say maybe choosing from keyword answers is really just a good way to be for doing the answering at the moment, because it's hard to know what else to do. So let's move on to the questions. So we know the common types of questions. What color is there? Is this what is the man? How many people? It's what is the man, not what is the woman, as was noted in the earlier talk. And you know, in some sense, these questions are a mirror of the answers, right? Because we have a lot of color questions, because we have a lot of color answers. But the main problem with the questions is that they're so short, that they're nothing but very simple facts. So over 80% of the questions are between 4 and 8 words long. And so the kind of questions you get is, what is she holding? What color is the napkin? Is the man wearing formal clothes? And even if you just try and ask a simple relational question like, is there a fountain in front of the building, then we're already out into the tail of 9+ words where there are very few questions. And so it seems like the big problem is in current VQA is that these simple questions about objects and attributes fail to test compositional language understanding and reasoning. So we're not really working on exploiting the power of language in this task. And so I think the obvious place to sort of move and make good progress is making moves on the questions. And so just coming up next, Drew is going to talk about the GQA task, and that's our first attempt to do that, to sort of push into a space of more complex relational questions. But I think there's then also opportunities to expand by using different images. That overall the MS COCO images don't describe very complex situations. And there are a lot of more complex situations in the world. And if we started having more of those in the images, I think we'd be able to ask much more interesting questions about different environments. This isn't the only way to go. I mean, another interesting data set is NLVR2. I won't say much about it, because since Yoav Artzi is meant to be I presume he'll talk about it when he talks at the end of the day today. The goals are very similar, wanting to go beyond these sort of simple object and property questions. And so an example of a question is on the right side. So there are 2 pictures, and there's the statement, both images show a silver pail being used as a flower vase, as they say in this country. So interestingly, this data set is sort of adopting the strategy I was suggesting. It's not trying to change the answers to be difficult natural language. In fact, they're all yes-no questions. So in that sense, it's kind of like natural language inference data sets in the NLP community. But it's exploiting the fact that you can have an easy set of answers, but arbitrary difficulty in the question or statement that you have to answer. On the other hand, I think there are some things about this data set that are a little bit quirky. So the two-picture format, I think, is sort of a little bit weird as a natural task. But more on that probably later. What's still missing? And I think for going beyond that, for what's still missing, is we really have so much more to do in deep understanding and being able to work out how to reason in much more abstract spaces. And I think VQA is a perfect space where there's still a lot more that can be done in coming up with novel architectures that push us towards more abstracted reasoning, and to a fair measure that hasn't yet happened. So my exhortation for next year's VQA is, rather than making the dimensionality of your model bigger or using BERT version 2, that I think there is still opportunity to look for model architectures that are doing much more reasoning in abstracted spaces. And I'll tell you a little about an attempt at doing one of these that we've made in the end part of the talk. So, getting finally to the V, I think what we should be seeking is visual abstraction, which means that we're heading more towards using a language of thought. And so essentially my argument is that I'm a bit nervous saying this because I'm not actually an expert on human visual perception, and there are probably lots of people in this room who know more about human visual perception than I do, but I'll try it out anyway. So I think most of vision, vision people make the analogy about V1, V2, and V3 and low-level visual perception and how the neural nets are modeling that, and that's great. But the fact of the matter is that human visual understanding quickly moves above that level, and human beings create and use very abstracted models of what is perceived, what are sometimes called scene gists. So that in terms of what human beings get out of a single saccade, that they're not actually seeing most of what's in an image. They sort of maybe have some focus on particular things. They see the overall scene. They see this is outside countryside. There's a man, and maybe if they're seeing him a little bit more closely, he's got a bicycle helmet, a watch and gloves, there's grassland, a cow. That's sort of all they're getting out of the image, right? That they're not seeing all of the details of the image. And I mean, there are lots of human experiments that show these kind of things, that you can make huge manipulations of images in pixel space, and that human beings don't perceive them at all in their sort of conscious reasoning. So my thinking is that we want to be doing more of something like that. So we want to be making use of concepts that organize our sensory experience and building a semantic world model relating these concepts as a sort of an abstraction of our visual views. And this will allow us to generalize much better from examples and to more effectively draw inferences about visual scenes. So one data set that has attempted to give a version of an abstracted semantic representation of scenes is Visual Genome by my Stanford colleagues, Ranjay Krishna, Michael Bernstein, Fei-Fei Li, and a cast of others whose photo I did not stick up. So the idea of this is that you have objects like the cow and the person, the watch, and clouds. I mean, of course, since this is vision, you don't actually only have those objects. You have a ton of other objects being recognized, but I'll keep it simple. So we have the objects, and then Visual Genome has a sort of a simple ontology where the objects have attributes like a silver helmet and a black watch and green grass, and then you have relations between objects. A man is kneeling on the grass, the cow has a bell, and things like that. So what we'd like to do is have models that more operate in this space. So the hope of deep neural models is that they're learning higher level abstractions, and that those abstractions can disentangle factors of variation, improving generalization. But I think we haven't fully realized this hope in terms of the kind of current deep CNN stacks that are typically used for vision, and that there's more to do with that. And I mean, in particular, a very powerful notion has been this notion of attention, that's been super useful over a lot of deep learning models. But what seems like it'd be a very good idea for pushing to these abstracted visual representations is to be having attention not over images, over pixel space, but rather having attention over a concept space. And that's the kind of model that I'm going to talk about in a moment. This is fairly closely connected to some of the ideas that Yoshua Bengio has been talking about when he talks about his consciousness prior, though I don't altogether like that name, that the suggestion is that there's a deep representation that disentangles abstract explanatory factors, but then what you're doing is you're using an attention mechanism over that deep representation. The version I'm about to present, which is work by Drew, is a bit different to that, but it has some of the same ideas of trying to do attention over an abstracted space. Okay, so the idea of this is that we have a vocabulary of embedded concepts, which are our atomic semantic units. And essentially, that's a cleaned up version of the visual genome ontology. And the crucial difference from most work is that we're going to translate both things in the image and things into the question into the same language of concepts. And so both sides will be being represented as attention over the concept vocabulary. And in some sense, this is meant to be capturing some of what I was saying before about human beings. So what do we do? So given an image, we construct a scene graph. And then we're going to treat that as a kind of state machine, giving us a neural state machine, where the states of the objects and the transitions correspond to relations. And then what is a state? A state is going to then make use of attention. So it's going to have attention over what kind of object it is, and attention over different properties, both of which are represented softly as attention distributions, but in a fairly peaked manner, so that we can have something that there's an object that seems to be a girl, and then we can be saying something about different attributes of the girl. And so these properties give us a disentangled representation. So then if we have a question, we're also going to interpret the question as a series of instructions over these same concepts. So we're going to take the question words and use an attention-based decoder, produce a series of concept attentions that's representing the question. So for what is the red fruit inside of the bowl to the right of the coffee maker, the encoder decoder is going to translate that into these attentions over concepts. Coffee maker, right, bowl, inside, red. And we're then going to run this by simulating a computation of our neural state machine, feeding in an instruction at a time and traversing states over the semantic graph, so that we're starting off with the coffee maker, it's hard to see here, then moving to the right to the bowl, looking for things that are inside the bowl, and looking for something that is red, and that's giving us the answer of the apples. Here's one more example. What is the tall object to the left of the bed made of? So then we can start with the bed. Oops. We can start with the bed, look to the left of it, see something which is indeed tall, a tall cabinet, and ask about its attribute of what it's made of, and return wood. Okay, so here's one set of results to show that this actually does something useful in terms of disentangling and allowing reasoning in terms of concepts. So this is some results on the VQA-CP dataset by Aishwarya, wherever she is, Agarwal. That the idea of this was it was a sort of reweighted train test data sets picked out of VQA so that you get different distributions between train and test. So for the what sport question in the training data set, the most common answer is tennis, whereas in the hard to read. In the test set, the most common answer is skiing, and then you have baseball and soccer, so it's all different. And what she and her colleagues showed is that for models of VQA available at that time, they fell apart once you changed this distribution. So Jacob Andreas's neural module networks or the stacked attention networks, that their performance dropped basically by half once you changed the distribution between train and test. Okay, so here's testing out this model and some others now on version 2 of VQA-CP. So here again are the stacked attention networks, hard attention networks. This was the model proposed in the paper. In a way, the model proposed in the paper, VQA, is sort of doing what I've been talking about, because it did put attention on concepts in both the visual and the language space, but it didn't have the kind of sequential reasoning that's in the model that I'm presenting. Here is a whole bunch of 2019 archive papers, maybe some of them are here, that are better, but we really do actually get significantly better results again, and we think that this sort of abstracted reasoning over concepts as a multi-stage compositional reasoning over concepts gives you the power of disentanglement in a good way that lets you do better at reasoning problems over pictures. Okay, so that's mainly what I wanted to present. So here are my quick summaries. So for VQA, these are language, but I really think a promising way forward is to think about how to work in a much more abstracted language of thought space for the entire problem. And I think that, there are a lot of ideas that might be pursued in building neural models that make much greater use of abstraction and are simulating not only V1, V2, V3 in their image pipeline, but are actually simulating what happens in human visual understanding at much more abstracted levels. I think we should be looking for tasks that really require understanding and multi-step compositional reasoning, and there's started to be work on much more interesting tasks, but I think there's still more that could be done there. And I'll encourage all of you to build networks that think. And I'd like to suggest that this idea of iterative attention over abstracted concepts is a powerful way of starting to build new neural networks that think. Thank you.
Thanks, Chris. Questions?
Hi, thanks for your talk. I really like this idea, but I'm wondering if you have thoughts on what level of abstraction our language of thought could be. I mean, most of the arguments given, about language of thought have been generally kind of hand-wavy about, well, there's a person, and the person has components, but how do we, as for annotators, decide on the level of abstraction we want in order to fit these things into our models?
Yeah, so that's a good question. So for the scene graphs of visual genome have a very simple ontology, right? They're objects, they have properties, and there are relations between them. Putting on my somewhat dusty linguistic semanticist hat, honestly, I think that ontology is too simple, and there's stuff that it just doesn't account for. Among other things, you can't have properties of relations, and that would seem useful, and that there's sort of more fine-grained things about the nature of images that you kind of can't also easily capture as, objects and sub-objects and their properties. On the other hand, I think it's not actually such a bad cut as a hit the easy 80% of the problem. And I actually think that, it's not a bad place to start, and there's a lot that we can do by working with that ontology to capture a lot of what humans see in scenes. So I kind of really think we could push things a lot just using that before it actually becomes the limiting problem that we don't have a good enough representation of an abstracted scene.